Imagine, for a moment, that you are watching and listening closely. In the stillness of a starry night, a lone telescope peers into the darkness above. On its sensor, amid countless distant suns, a tiny speck of light glides where no familiar orbit should carry it. It is not circling the sun like a local comet. It is cutting across the solar system on a path that begins in interstellar darkness and will end there again. A hush moves through control rooms and observatories worldwide. A visitor from another star has arrived. Only the third of its kind we have ever seen. It has a name that sounds like a secret signal. 3I/ATLAS. And with it comes a question as old as curiosity itself. What story does a stray from another sun bring to our doorstep? Tonight, we follow its trail to learn whether it will offer answers about the building blocks of worlds, or deepen the mystery of how solar systems are made and unmade. And if you'd like to help me bring more of these mysteries to life, don't forget to like, comment, and subscribe. The first chapter of this story opens in July 2025, when a survey telescope built to protect Earth from incoming asteroids notices something that doesn't behave like an Earth-bound threat at all. ATLAS, short for Asteroid Terrestrial Impact Last Alert System, scans the sky for motion, catching subtle shifts against the fixed constellations. On a routine pass, the software flags a wanderer that doesn't fit the template. The follow-up images show a dim, fuzzy halo, a coma, the calling card of a comet. But the orbit solution, those first fitted curves through the new positions, tells a stranger tale. The path isn't a closed ellipse like an asteroid or a bound comet. It is a hyperbola, a one-time visit, in and out. The newcomer earns the designation 3I/ATLAS, third interstellar object discovered, found by ATLAS. The news moves fast. Almost as quickly, the telescopes move faster. If you remember our first visitor, Oumuamua, you'll recall how it slipped into the inner solar system and was recognized too late for deep study. The second, Borisov, looked every inch a classic comet, just not from here. 3I/ATLAS arrives early enough that astronomers can prepare point-based telescopes, schedule spectrographs, coordinate ground-based observatories across longitudes. The first thing that startles the careful eye is how alive it already seems while still far from the sun, out beyond Jupiter's orbit, where the light is thin and the cold is industrial. The object glows with a coma. That implies something volatile. Ices that vaporize at very low temperatures are already escaping its surface. Imagine a freezer that fogs before you open its door. That's 3I/ATLAS, outgassing in slow motion across the deep. Spectra peel back the light and lay bare the chemistry. Instead of the usual dominance of water ice that most comets reveal once they warm, 3I/ATLAS appears unusually rich in carbon dioxide ice, dry ice on a planetary scale. That single fact, deceptively simple, unlocks many doors at once. It explains the early activity. Carbon dioxide can sublimate in sunlight that water shrugs off. It hints at a birthplace where temperatures and pressures favored the freeze-out of CO2 more than we're used to, or at a long, slow baking history near a parent star that drove off other volatiles, leaving the carbon dioxide fraction high. It also means this is not just a comet from another system. It is a comet with a different internal recipe, a frozen page torn from an alien cookbook. As observations stack up night after night, the picture sharpens. The coma breathes with the sun's warmth, gas jets flicking dust into space. Heavy atoms hitch rides too. Tiny signatures that say the nucleus is not a single uniform block, but a mixed geology. Rock, dust, ices layered by time and heat. The nucleus itself remains hidden inside its own atmosphere most of the time. A compact body perhaps on the order of a kilometer across, battered and ancient. If Oumuamua felt like a cryptic whisper and Borisov like a hello from a familiar cousin, 3I/ATLAS is a resonant voice. Bright enough, active enough, and early enough to study in depth. For planetary science, that's gold dust. The dynamics are as captivating as the chemistry. A hyperbolic orbit means the sun is a tourist attraction, not a home. At closest approach, 3I/ATLAS will scream past at tens of kilometers per second, far above the solar system's escape speed. Its trajectory is steeply inclined relative to the planetary plane, as though diving in from a tilted lane of the Milky Way's traffic. Where did that path begin? Trace the arrow back and you arrive not at a single star we can confidently name, but at a region and an era. The odds point to an origin amid older stars, the galaxy's thick disk population, where the fossil record of the Milky Way is written in slower, inclined orbits around the galactic center. If so, the comet's frozen heart could be older than our sun by billions of years. Imagine material that condensed around a different star when the galaxy was younger, now arcs through our skies. The word ancient suddenly feels too small. How does such a traveler get set loose? Think in billiards. In a young planetary system, giant planets patrol the outskirts like celestial bouncers. A close pass can redirect a comet into a longer, looser orbit. A closer pass can eject it altogether. Star-to-star flybys in crowded stellar nurseries do this too, shaking the jars of comets and spilling some into interstellar space. Once free, a comet drifts between suns in frigid darkness, tugged a little by this star, a little by that, for eons. Occasionally, chance aligns a path toward one star's inner sanctum. In 2025, that star is ours. The calendar matters. Because 3I/ATLAS was discovered months before perihelion. Researchers can choreograph a campaign. Ground telescopes catch it in southern and northern skies as the geometry changes. Space telescopes isolate its spectra beyond atmospheric interference. Planetary missions, those robotic emissaries already cruising the inner solar system, check their sight lines and power budgets to see what snapshots they can steal as it passes. Even Mars might become a relay mirror of sorts, with orbiters there positioned for a different vantage when Earth is too close to the sun's glare to watch. It's as if the solar system's existing fleet has been repurposed into a chorus of listeners, each in a distinct seat in the theater. With that chorus, details emerge that are easy to miss at first glance. The coma's brightness waxes not only with decreasing solar distance, but with the changing angle between sun, comet, and observer, sculpting the tail's geometry. The jets aren't steady. They flicker as the nucleus rotates, exposing different vents. There's a cadence to it. A rise, a fall, a pulse, whispering the rotational period. The dust size distribution, the mix of talc-fine grains and sand-like specks, can be teased out by how the tail scatters light at different wavelengths. Each of these measurements is a thread. Together they weave a portrait of surface layers, porosity, and thermal history.
The deep mystery, and the part that makes scientists lean forward, is the way 3I/ATLAS forces us to recalibrate our mental models. We used to think of comets as snowballs laced with dirt. Then we learned they are more like fragile layers of porous ice and dust that remember their heating cycles. Now, we are confronted with a version assembled under a different sky, weighted toward carbon dioxide ice. Which possibility is truer? That its home system's protoplanetary disk had a different chemical inventory, or that its history near its star selectively boiled away certain ices? Analogy helps. Picture two bakeries using the same recipe, but different ovens. One hotter, one milder. The result can look similar. Bread is bread, but the crust and moisture inside diverge. 3. I/ATLAS is a loaf from a bakery across town, and by tasting it, we can tell something about both the ingredients and the oven. Every good mystery invites competing theories, and 3. I/ATLAS has a table set with several. The conservative line says this is a normal comet by interstellar standards, one we simply haven't met before. They could be CO2 rich if they form beyond the water's snow line under colder conditions, or if thermal cycles drove off other volatiles and left dry ice dominant. A second view emphasizes age. A very old nucleus, thermally processed over billions of years, might have sorted its ices by volatility and structure, preserving CO2 in protected pockets, while other ices sublimated away from exposed surfaces. A third thread looks to structure. If the nucleus is highly porous, sunlight can penetrate deeper and liberate CO2 from beneath a thin crust, giving outsized coma brightness far from the sun. Each of these has supporting data and drawbacks. The first must explain why we don't see many like it in our own backyard. The second leans on a conjectured ejection time so far in the past that random kicks and spins could have altered the surface in unpredictable ways. The third depends on subtle balances between pore size, heat conduction, and gas diffusion that are notoriously hard to measure. Then, there are the fringe ideas, the ones that headline writers love but data seldom support. Whenever interstellar objects appear, a small but vocal chorus wonders if we have stumbled upon probes, silent, watching, maneuvering. Oumuamua's non-gravitational acceleration, coupled with its lack of visible outgassing, poured gasoline on that speculation. With 3I/ATLAS, the glow of a coma, the gas signatures, and the evolving tail are all classic hallmarks of a natural comet. There's no need to invoke engineering when sunlight on dry ice will do. Still, it is worth remembering why such ideas persist. They are a measure of how extraordinary it feels to witness a visitor from another star. The idea that the cosmos might be talking back to us is deeply human. The discipline is to let the data speak first and loudest. A different speculative lane, older and quieter, asks whether interstellar comets could shuffle the deck of chemistry between star systems. Panspermia, the notion that life, or at least life's precursors, can spread by natural couriers, sits here. Controversial, but not absurd. What might survive in a comet's deep interior for eons of interstellar exposure? Organic molecules are hardy. Complex ones can form in cold environments under radiation, and then hitch rides inside grains of dust. Microbes are far less likely to endure the combined assaults of deep cold, vacuum, and radiation for millions of years. But the thought experiment persists because it binds together three truths. Comets are carriers. Interstellar space is not empty, and planetary systems are not as isolated as they seem. Whether or not life hits a ride, chemistry surely does. There's also a subtle philosophical turn in this story. For most of human history, stars were distant, unreachable. Our age can launch machines into their direction, but not yet to them. And yet, 3 times now, Pieces of other star systems have come to us of their own accord. If you think of exploration as a dance, this is the cosmos taking a step toward us. By studying 3, I/ATLAS, we do more than learn about one comet. We practice how to learn from all the others that will follow. We refine strategies, how to quickly mobilize telescopes, how to split scarce observing time, how to pull signals out of glare, how to compare notes across continents. We test technologies, rapid data reduction, automated alerts that catch unusual orbits, target of opportunity modes for spacecraft already en route elsewhere. The next time an interstellar visitor appears, we will be faster, sharper, hungrier. Comets have always been timekeepers. In ancient chronicles, they were omens, marking years with their sudden spears of light. Today they are archives, keeping time in layers of ice and dust. 3. I/ATLAS carries a timestamp older than our calendar can hold. Run your finger along that imagined core, and you're reading a braille of cosmic weather. Passages near a long-gone sun, epochs of deep freeze, sudden expulsions, gentle rains of dust. Its path through our solar system is a brief caption in that long text. As it approaches the sun, we may see its activity spike, jets brightening, the tail growing, perhaps even cracks or fragments as internal stresses exceed the strength of its frail structure. Many comets do this. It is a reminder that they are not marble statues, but brittle conglomerates held together by cold and time. If 3I/ATLAS splits, it will pain us a little. Who wants to watch a messenger break? And yet it might show us more, revealing fresh surfaces like pages torn open for us to read. In the weeks surrounding perihelion, some spacecraft will have vantage points Earth cannot. Solar observatories can watch when the comet is lost in daylight from the ground. Probes in deep space may glance sideways across the coma's veil. Mars orbiters could capture a view with the red planet glowing beneath, and the interstellar tail a glassy thread in the sky above. Even if the geometry conspires to hide the best spectacle from the unaided human eye, the instruments will see, and through them so will we. There's a quiet thrill in that, a planet-wide relay of attention, humans and machines synchronized on a tiny visitor. When the comet recedes, the data will remain. Spectra, light curves, image stacks, time series, and wavelengths our senses can barely imagine. From those, we'll draw maps of temperature and texture, of gas mixing ratios, of dust grain sizes and velocities. We'll compare them to comets born with our sun and see the overlaps and the departures. We'll feed them into models of planet formation and other systems, update our priors, tighten our error bars. Perhaps the most lasting outcome will be a shift in expectations. Once you know that interstellar comets can be bright, CO2 rich and detectable months out, you can design searches that assume that richness. You can plan interceptors to wait in ambush. You can write proposals with the confidence that targets will come.
If all of this feels grand for a smudge of light in a telescope, consider what hangs in the balance. Our sense of whether the solar system is ordinary or not. If most interstellar visitors resemble Borisov and Atlas more than our local comets, then our neighborhood may be unusually water-rich. If many turn out to be chemically diverse, then planetary systems may be experiments, not replicas, each set of worlds flavored by its own disk history. Either way, the answer bears on the most human question of all. How common are the conditions that gave rise to us? We don't need certainty to feel the weight of that question. We need trajectories, spectra, patience, and wanderers willing to cross the dark to meet our gaze. There is a final image I can't shake. Picture 3. I/ATLAS from far behind, its tail pointing sunward, its head shrinking to a mote as it outruns our concern. Somewhere ahead lies nothing in particular. Just the shared gravity of 100 billion stars, a stitched fabric of weak pulls. Perhaps in 10 million years it will wander within a light year of another sun. And all of this, our telescopes, our calculations, our awe, will be as irrelevant to it as the heat it borrowed from our star. But we will still have been changed by its passing. We will have listened closely to what it had to say, and in the listening learned a little more about ourselves. That we are a species who builds instruments to extend our senses, stories to extend our meaning, and questions to extend our reach. So here, at the edge of its visit, we pause. We've traced its discovery, its chemistry, its flight. We've weighed the sober theories and nodded politely at the speculative ones. We've asked what it tells us about stars we will never see up close. And we've admitted that some mysteries remain. Where did it truly begin? What did it witness on the long road between suns? What other recipes for worlds does the galaxy keep in its pantry? These are not questions we can answer tonight, but they are the right questions to ask. If you step outside after this and look up, the odds are you won't see 3 I/ATLAS with your naked eyes. You may see a familiar planet, a bright star, a passing satellite. Yet knowing that, somewhere in that black, a fragment of an ancient system is arcing past our sun changes the sky. It makes it a place of exchange, not isolation. It reminds us that in this universe, the unexpected is not an exception. It's the rule. The cosmos is busy, and sometimes, through no effort of our own, it sends a gift. The least we can do is meet it with attention. And so I'll leave you with this. Will the secrets of 3 I/ATLAS help unlock the story of our own cosmic origins? Or will they entice us toward deeper enigmas we haven't yet imagined? Tell me what you think in the comments. Because tonight, a messenger is passing through, and the next may already be on its way.